Hello, my people. Welcome back. So I did want to talk today about gas laws. I pretty much just made a whole 10-minute video, and then my computer was like, "Nope, sorry, you have to do that again." So I have a bunch of notes here, but one thing I wanted to talk to you guys about before we get started on some of the um, uh, gas law stuff is how pressure relates to altitude. So let's say we got Mr. Moshe is here at sea level, and think about all the gas particles above me if I'm at sea level. Okay, there's a bunch of gas particles above me. And then let's say Flom decides to climb Everest. So Flom is on Everest right now, and she doesn't have as many gas particles above her, does she? Okay. So you can think about in gas pressure, the higher the pressure, the more gas particles are above you, pushing down onto you. It's like if you had rocks like back in the olden days when they used to stone people, like the more rocks on you, the more pressure. Okay, the more gas particles on you, the more pressure. That was a really stupid um, analogy. But now, if I'm at sea level, I have the usual amount, and then let's say Adam Jin is down here in Death Valley. Okay, so Adam Jin, because he is closer to the center of the Earth, he has way more gas particles on him. So he is going to have a higher pressure. So I'm going to have a normal air pressure, so about 760 mmHg, about 760 mmHg. Jin is going to have higher than 760 mmHg, and Flom is going to be much smaller than less than 760 mmHg. Okay, now real quick, I want you to take a moment to consider all of these. So I just stopped the video and I want you to think about what effect each of the temperature, volume, and amount of gas have on pressure based on what you know. The two things that you know affect pressure is the amount of collisions with the walls of the container, and two, the force which with the gas particles collide with the walls of the container. So, and then temperature and volume, I want you to think about if you leave a basketball outside in the cold or in the heat, what happens to that basketball, or even a balloon. All right. And then for this one, I want you to think about a balloon, blowing up a balloon versus letting a balloon out. Okay. Factors affecting pressure. Bowie. Under pressure. Okay. So the amount of gas. If I increase the amount of gas particles, I'm going to increase the amount of collisions with the walls of the container, okay? Because there's more particles to collide with the walls of the container. If I increase the volume, I'm going to decrease the pressure, because if I have more space, there's going to be less of a likelihood of these gas particles hitting the walls of the container. If you have less space, there's going to be, here you have less space, is going to be less of a chance, a higher chance of the gas molecules hitting the walls of the container. Less space, more collisions. More space, less collisions. Okay, and then temperature. Temperature directly affects the kinetic energy, so the speed of the so it also affects the speed of the gas molecules. So if I increase the temperature, I'm increasing two things. I'm increasing the amount of collisions because they're moving faster, and since they're moving faster, the force with which the gas molecules collide with the walls of the container. So temperature increases pressure, and that an increase in pressure equals an increase in temperature. So two of the units I didn't talk about yesterday are torr and psi. Torr is just the same as mmHg, and then psi is the American unit. All right, Boyle's law. Boyle's law states that if you have a constant temperature, and this is key, you need to have a constant temperature for this to be true, okay? If the temperature is fluctuating, then that's a confounding variable. You can't really determine anything if the temperature is changing, okay? As the pressure increases, okay, say we can think of a tire. As the pressure increases, the pressure in the tire increases, the tire expands. Typically, I would be inclined to switch these. So I would be inclined to say, as the volume increases, the pressure decreases. I would say, personally, pressure is a function of volume rather than the other way around. So your example says a balloon contains 30.0 liters of helium gas at 103 kPa. What is the volume of the helium when the balloon rises and the pressure is only 25 kPa? So P1 is equal to 103 kPa. Okay. P2 is equal to 25.0 kPa. Okay. V1 is equal to 30.0 liters. V2 is equal to question mark. Now, is V2 going to be higher or lower? Yes. If you said higher, then you would be correct. Okay. So P1, V1 equals P2, V2. V2 is equal to P1, V1 over V2, P2. Okay. So then, boop, boop, you're going to get V2 is equal to 30 times 103 divided by 25, which is, give me a sec, 30 times 103 divided by 25 is V2 is equal to 123.6 liters, okay? Charles's law. So Charles' law states that if the pressure is constant, so now in Charles' law, you need the pressure to be constant, okay? As the temperature of a gas increases, the volume increases. So now I want you to think about like a basketball. If you when I was a kid, I used to always leave my basketball outside, and if it was hot out, like in the summer, the basketball would actually expand, and it would get this like protuberance, and that was because the walls of the basketball couldn't handle all of the pressure, and so the volume would increase. So then, and then if you left it out in the cold, then the basketball would shrivel up. Okay, so the volume would decrease. In this case, you have a balloon inflated in a room at 24 degrees Celsius, has a volume of 4 liters. The balloon is then heated to a temperature of 58 liters. What is the new volume if all of the pressure remains constant? Now, before we start this is so important. Temperature has to be in kelvins always. So kelvins is just degrees Celsius plus 273. So in this case, our T1 is 24 degrees Celsius plus 273 is equal to 297 kelvins. Okay, our T2 is equal to 58 degrees Celsius plus 273, which is going to be 300, I can do math, I swear, 331 kelvins, okay? And then V1 is equal to 4.00 liters. V2 is equal to question mark. And then all you got to do here is a little bit of simple algebra. So in this case, you have V1 over T1 equals V2 over T2. So V1 over T1 equals V2 over T2. Another way, if you want to write it like this, you could say V1 T2 equals V2 T1. It's up to you. I'll probably just write it like this. And then, so now you just got to plug this in. This is not difficult. So V2 is equal to 290, V2 is equal to 4 divided by 4 liters divided by 297 kelvins times 331 kelvins. So you're going to get V2 is, I'm going to bust out my calc for this one. 4 divided by 297 times 331, 4.46 liters, okay? And that makes sense. Make sure your answer makes sense. So the temperature increased, so the volume increased. Yeah, that makes sense. And then Gay-Lussac's law. As the temperature of an enclosed gas increases, the pressure increases, okay? So like that basketball, the pressure was so high that the volume, the volume had to increase to correct for that. Now, don't forget, still need to be in kelvins. Need kelvins. Always. Always, always, always for gas law problems, temperature's got to be in kelvins, okay? No exceptions. Now, the gas in a used aerosol can is at a pressure of 103 kPa at 25 degrees Celsius. If the can is thrown into a fire, what will the pressure be when the temperature reaches 928 degrees Celsius, okay? So the pressure should increase because the temperature is increasing, right? So we're going to go P1 over T1 equals P2 over T2, okay? So we're going to get P2 is equal to 103 divided by 298, because I'm in kelvins here, times 928 plus 273 equals 1201 kelvins. Okay, so then P2 is going to equal 415 kPa, all right? Combined gas law. I'm going to have you guys actually watch some videos on that later. Okay, so we'll get to that. But that is it for today. Have a wonderful rest of your day. Be good to each other. Bye. I miss you guys.